Thank you very much for the kind invitation to come to India. It had been 10 nice days here, and I'm looking forward for the next days here. And I like to talk on a subject which I got interested some years ago, and I still think it's very fascinating, despite the fact that it's at the moment lacking a kind of deep theories like we had seen in all this Galar representation and so on. And I'm pretty sure that behind of this there is deep arithmetic, but at the moment it is just playing with Q series and finding identities. And okay, you see the formulas may come quite involved, and in particular we also see that it is deeply related to modular forms. And part of it is joint work with Henrik Bachmann, and also for the later part, it is work in progress with Leila Schnaps. Okay, let's begin, and I hope this works. Yes. Okay, multiple zeta values are real numbers that are given by this sum over cones of integers, and then you have these reciprocal powers, and we assume that all these indices are integers. And this is called a multiple zeta value, and then it's quite easy to see if you multiply two such sums, then it can be given as a linear combination of similar sums, and this shows you quite easy that this will be a Q algebra. And there's another way to express these numbers by means of iterated integrals, and then this gives you another way, which is called shuffle product, to express the product of these real numbers. And then you have two ways to describe the same product, and this means you get a linear relation. So for example, if you multiply 2 and 3, then it will give you this. If you multiply according to this rule of multiplying these nested sums, and if you multiply this in the representation of iterated integrals, you get this expression, and then the idea is that these two numbers, these two sides are the same, and then you can solve and you get some relation. And now multiple Q zeta values come from the idea that once you have some nice objects in natural numbers, then you'd like to deform these numbers by a formal parameter Q. And the rule is, as soon as Q goes to 1, you should get back your identity of natural numbers. And this occurred first in the work of Gauss on binomial coefficients. And he introduced the Gauss Q integer, which is 1 plus Q plus Q to the n. And obviously, if Q goes to 1, you have n summands, this gives you 1. And also it has the nice representation that is just the geometric series where you just subtract the n, Q to the nth power again. And so this is the better way to. Now we can get multiple zeta values. So we just replace n as Q integers, but then we see we have a double denominator, and so we forget at the moment, and this is why we call this modified. And then also, this won't be a Q series which has any point of convergence, and therefore we just enforce that the first of these polynomials is vanishing at 0, and therefore we get some well-defined formal Q series which has value 0 in Q equals 0. And now, if we plug back in again the factors we have neglected here, and taking the limit, we really recover this multiple zeta value with the same index, and we have a large freedom by choosing these polynomials, and essentially this freedom is that we have to consider the values in Q equals 1, and for reasonable models you just choose these polynomials so that the value at 1 is 1. Okay, and now you can make again a vector space of all these multiple q-zeta values, and you want the constant also to be a multiple q-zeta values. If you have no index and no polynomial, it should just be 1. And then it's quite easy to see that if you multiply two of these objects, it will be again a linear combination of these objects. And for example, if you just make this formula here, then again, you make the same trick as you show that the nested sums for the multiple zetas give you a linear combination. You see this will be also giving you a linear combination of such things. And clearly the degree of this guy here is bounded by the index if the individual degrees have been bounded by the index. So we have a very nice definition of multiple q-zeta values. We have almost no restrictions, and we just easily get by means of nothing that we have a Q algebra. But the price we have to pay that with this description we won't get any reasonable analog for a weight and also for depth. And anyhow, we have a nice filtration on this space. Namely, we could require that these polynomials are bounded with respect to the index. So with respect to these indices, and then we could even bound these furthermore, and so we get this space ZQD, or we could require that all these polynomials should vanish in 0. Then we get what we call with a circ at the top, and then we could even intersect these two restrictions, and then we get a large set of subalgebras of this algebra of multiple q-zeta values. And why is this interesting? Because there had been several approaches to generalize multiple zeta values to q multiple zeta values, and most of these models just fit in this framework, and they just are subalgebras given by certain circs and Ds and so on. And so by Bradley, Shao, Schlesinger, Sudelin, Okunkov, and so on, all these people have studied particular multiple q-zeta values, and all these are contained in these models. And we are studying here something a priori different. So we study with B brackets. So these are Q series which are obtained by summing up particular polynomials, namely these Eulerian polynomials, which you get by considering this polylogarithm at negative values. So this will be a rational function. So it is a polynomial divided by some power of 1 minus t. And so we sum up over these guys where we plug in instead of t a q to the n. So we take a kind of elliptic averaging. And the new thing is that we allow in additional these indices to occur as powers in this sum. So in the previous, we did only have polynomials in T, but we did not have the summation index occurring in here, in this sum. So it's something different. And for example, if you look at small cases, you can write down these polynomials. They can be given in some recursion and so on. And if you write down this series, you get a feeling how they do look like. And for making the product description of these guys more beautiful, we just make some simple normalization factor in the front. Okay, so we have these guys, and let's look how they look like in particular cases. And in particular, if all these lower indices are 0, then we just save space and just write the bracket for these. And then these brackets are Q series which have a very nice Fourier coefficients, namely we decompose our n into L products. and then we want the products to be ordered by the first factor, and then somehow we take the multiplicity of each of these factors to some power determined by these indices. So in particular, you recover that in the case of L equals 1, this is nothing else than the divisor sum you know from the theory of modular forms. And so the K bracket is nothing else than the Q tail of an Eisenstein series of weight K, but be careful, we don't have any restriction that the K is even. So in this setup, we have what some people call Frankenstein series, because the Eisenstein series behave very nice, have a nice modularity, but if you make with the same procedure formal Q series, then it has a very weird functional equation and so on, and so it's a nice object within this theory, but not with respect to a modular aspect. And in particular, we had included the empty multiple q-zeta values by being constant in such a way that the quasi-modular forms are contained in this space. So we have now an algebra of Q series which contains the quasi-modular forms. So this is has to be considered as a nice object. And now we can look how do these spaces look like. And in particular, if we had this restriction that these polynomials all have to vanish in 0, then we just recover the brackets. So the subspace of the brackets is nothing else than the multiple q-zeta values which do have polynomials that vanish in 0. And then if we restrict now by bounding this degree, then it is nothing else than the subalgebra of these Q brackets where all the indices, let's say, are bigger than 2. And then you know that if you multiply these, then they will give you a subalgebra. And moreover, the first space is closed by differentiation, and it is a conjecture that the second space is bounded by this, or it's closed by this differentiation, and this might have some implication in Gromov-Witten theory of Okunkov. So he is identifying this multiple Q series as generating series of certain Gromov-Witten invariants, and then this differentiation corresponds to some action of the tension bundle and so on, and he wants to have this closed, and which boils down to this combinatorial question whether this space is closed by this Q derivation. Okay, and why are these B brackets interesting? They still give back multiple q-zeta values, but we have to a little be careful. So if we take this limit, then we get this multiple zeta value shifted by the lower entries. So in particular, if all these lower entries are 0, we just get back this multiple zeta value, and if the entries below are bigger, then we get some shift. Okay, and later I will shortly remark that there's a nice motivation why to study such Q series, but at the moment it's just because they are here and they are nice objects. Okay, and now the first result is that despite the fact that these B brackets have an a priori different look because you have these indices occurring in this Q series, you can still prove that they give you a spanning set for all these multiple q-zeta values. And the trick is quite easy. So let's make the proof by example. So let's look at this B bracket 1101Q. So this is writing down the formula, so we do almost nothing. But now, how we get this N2? So this N2 we write as 1 plus n2 minus 1. And so the 1 is here. And how we get the minus 1, the n2 minus 1, it is here. Because this is nothing else than 1, because nobody asked us that these q in the polynomials on the numerator has to be co-prime to the denominator. So we could just have that you get this kind of expression, which is just introducing a 1. And so you sum up over just the new indices n3. And the sum of these up to n is just n2 minus 1. And this tells you that for this particular example, you can write this q series, which has a priori a completely different shape, because here you have this n2 in the sum, can be written as a linear combination of these multiple q-zeta values, just in the sense of the definition we had seen at the beginning. And now why we propose to study these p brackets? The point is now for these p brackets, you have a very nice notion of the weight, so which will be just the sum over all these indices. And also you have a nice notion of the depth, which is just the set, the number L, where L denotes this number of double indices. And so I'd like to propose that this is a nice spanning set for this algebra of multiple q-zeta values, and they are nice because they have a nice filtration by a depth and by a weight. Okay. So they have furthermore nice properties, and one of the nice properties is that they fulfill dimorphy, which is the technical expression for the fact that you have one product and you have two formulas to express this product on the level of representatives, and this then gives you identities on the quotient. And so you have these two ways, and in particular one can show that this is the lift of the Staffel and the Shuffle. And so this is a theorem by Sudilin, and somehow that it lifts. The shuffle is the way we found that you have this product stuff. So you have now the feature that you can lift multiple zeta values, and you can lift these two descriptions of the product. And another nice feature is that if you don't understand an object, then if you had listened often enough to Zagier, then you should make the generating series. And in most times, if you have a natural object, if you study the unity of all these objects, then you get information back to the single one. And in this case, we consider the generating series, which we denote by these brackets. And so we just take the sum over all these q series, and now we multiply these with these polynomials, where the degree is depending on these indices of these q series. And then it was observed by Zagier in the depth 2 case, and then generalized by Bachmann to the depth L case, that you can rewrite this in the formula which is much more neat. So it's really it's a nested sum, and then it's a product over these exponentials, and it is really something you can work with. And now you can multiply, for example, two of these generating series, and to see how this multiplication will look like. And so the point is that if you multiply two of these generating series for this depth 1 guys, then you get these depth 2 guys, then you get the difference of some depth 1 generating series where you now have a shift of the variables, but then you also have to divide by this x1 minus x2, but observe if x1 equals x2, then this has a 0, and therefore this is in fact again a power series in this polynomial variables x1, x2, y1, y2. And now furthermore, you have a kind of additional terms which take into account that the multiplication is not graded but filtered. And here you see Bernoulli numbers coming, and this is nice. And also you have a different symmetry, and the symmetry is that if you have this generating series for the depth L guys, then you can interchange the upper and the lower indices according to a rule which is called swap invariance by Ekal. So you have a kind of upper triangular matrix, and it's inverse, and they give you a symmetry on these objects. And if you write this identity out, so you now can make an expansion of this, and then you take the coefficient. You know, two power series are the same if the coefficients are the same, and then you see that on the individual object, the swap means in depth 1 that you just interchange the upper and the lower, and then you have to shift it by +1, and you have to subtract by -1 downstairs. In particular, this makes sense because this could be 0, and therefore it will be at least 1 here. And on the other hand, this will be allowed because the S was assumed to be bigger than or equal than 1, and so it could be at worst 0, and so it would be fine again. And if you apply this for a depth 2 guy, then it suddenly immediately becomes quite nasty and big. So you have these symmetries, and so this distinguish somehow this model amongst other models for multiple q-zeta values where you may have just a rule of multiplication, but you don't have the second symmetry. And this is somehow a particular point. And now we are in the position to define how we get this double shuffle. So we had the ordinary product, and then we had this involution P that's coming from this partition relation. And then we can just apply this involution to the factors of this product, and then we apply it outside again. And again, remind you, we are working on the level of representatives, and therefore the image of this involution is just an expression of the same element, but now with different representatives. And therefore it really gives you an identity which is a priori not clear that this is a relation in your algebra. And for example, if you just write down something like this, and then Gisbert will reckon that writing down such example on the blackboard might be take very long. And, but you don't now really to understand why you have the 35/2 and stuff like this. It's just to give you an impression that you get formulas, and the formulas get quite big, and you need to understand these formulas more from a different, like a higher point, because the individual relation just says you nothing. And the conjecture by Bachmann is that all these relations of B brackets come from these kind of relations. Okay. And so actually, what we did is we found that there's a nice algorithm to calculate the Q expansion of these B brackets. And the best is you calculate many of them by time, and you can make this in a parallel computer, and you use lots of memory, and then you make big tables, and then you ask how many of them are in different weight and depths are linear independent, and out of these tables you try to find out pattern, and this is what led us to these conjectures. And so, for example, we assume, we conjecture that these multiple zeta, these q values, give you something that is isomorphic to a free polynomial algebra. We have them conjectures with respect to the vector space basis, so every B bracket is in fact a linear combination of brackets. So this means that by some miracle we could restrict to a smaller set. And even more, it's miraculous, is that we can even restrict ourselves to the brackets which only have 1s, 2s, and 3s as entries. This should be set next to a result of Brown for multiple zeta values, where he proves that if you consider the multiple zeta values which have only 2s and 3s as an entrance, then this gives you a spanning set for all multiple q-zeta for all multiple zeta values, and this is somehow, let's say, among the deepest results people know about these multiple zeta values for the moment, and it uses mixed state motifs and so on. And so we have a similar conjecture, but we don't have an idea how to prove this because we don't know what are the geometry behind. And also we have a conjecture for the graded dimension of this algebra. This looks a little bit more complicated, but later we will see that it's quite natural to have this kind of rational function. Yeah? Yes? There's homology. There's homology. So we will see quickly a more refined version of this. I hope I remember. Yes, it's on the next slide. So the actual conjecture we do have is now we have the weight filtration and we have the depth filtration. And now we could make the gradient between this, of these two filtrations. And then the statement is that the Hilbert-Poincare series of that object is given as a product of two power series in x and y, where the first one, now the people who had been here last week will see again, this is nothing else than the Hilbert-Poincare series for the space of quasi-modular forms, and we use the fact that the quasi-modular forms do not go beyond depth 2, because we know that every modular form or quasi-modular form is expressible as a linear combination of products of just two Eisenstein series. And so this is somehow ruling out the quasi-modular forms. And actually, this tells you something that the quasi-modular forms are a subalgebra of this algebra of multiple q-zeta values that has the same different behavior as the powers of zeta 2 have in the algebra of multiple q-zeta, of multiple zeta values. And now there's a second guy, and this second guy is a little bit longer than in the Protas-Kramer conjecture, but essentially what does it tell us? So we have generators in weight 1, and we have some derivation that once we have a generator, we have another one in weight plus 2. And we have relations in weight 2, and here it's nice to see that we see the dimension of the modular forms of SL2Z to the square. And so I think later at this point you should say, you see modular forms, that is interesting. Why do we get these? And the next point is, this is somehow seems to be the first occurrence where you see the square of the dimension of the modular forms. And this helped me to attract Sagier at some point. And then we have something which is belonging to homology, and this is the next one is extra generators. And so somehow these formulas can be understood, and I'd like to convince you that these rough expressions I gave you could get some meaning. Okay. And you could ask, okay, he's writing long formulas, does it make sense? And as I told you before, so we tested this with several thousands of these q-series. So it's something, if you calculate about over 10,000 coefficients of these q-series and you get some identities, then you should be pretty convinced that this is true. And so if you make a checkerboard and you just make the lines, something like the K and over the depths, and then we have something like this, and we have lots of points, several hundreds, and where we can prove that this is the same. But of course, if the depth goes too high, then the computer runs out of memory and so on. But it's we have more points to check than it's needed to write down this power series. So we really have some more information. And actually we can prove that for small weights, all this conjecture, a part of this conjecture is true. So in some sense we are able to prove theoretically some upper bounds, and by computer experiments we have a lower bounds because we can check easily whether two q-series are linear independent. So if they differ at a certain point in the q expansion, then they must be different. And so this is some evidence, and also to give you some more feeling why this should be related to modular forms, I'd like to make a quick excursion to the so-called multiple Eisenstein series. So these multiple Eisenstein series are just made in a similar way as you get multiple zeta values by summing over cones. And now here you sum over cones of lattice vectors, and you make this in such a way that you first define a positivity amongst the set of lattice vectors, let's say the one above the real line and the one to the right of the real line, and then you have some ordering, and then you sum these things up, and then the point is you get some q expansion, and in this q expansion you will get these multiple q-zeta values, and you also get multiple zeta values, and you get some powers of 2 pi I. And so, for example, the easiest case is, of course, the Eisenstein series you have seen before, but you also have these double Eisenstein series, which then you see they all fit together, and somehow these powers of 2 pi I are made such a certain weight is preserved in the context of real numbers. Okay, and now the result is, or the relation to modular forms is, you have this q-series and they are far off from being modular. And these relations in depth 2 should be seen as giving you a statement which non-obvious relation, which non-obvious linear combination gives you a modular form. And for example, if you take a Hecke eigenform, and then it has a period polynomial we've seen last week, then out of this coefficient of the period polynomial, we get some complex numbers by shifting this. And then the point is that if you plug in the suitable regularized multiple or double Eisenstein series, then you get a linear combination that expresses you this Hecke eigenform as a Q series. So you really see that this double Eisenstein series know somehow the Hecke eigenforms, in the sense if you make appropriate linear combinations to recover these things back again. And of course, we had this map going Q goes to 1 with this regularized enforcing factor, and then we just get back what people called the exotic relation. And now it's rather clear why this exotic relation somehow corresponds to these cusp forms, because they just express the cusp forms in terms of these guys here. And so we really have a nice lifting of these relations, and really it fits in this framework of these multiple q-zeta values. And the point is, so this gives you just a small proportion of all this relation we are expecting. And actually, if I talk faster, we will find that this relation can be seen in the tensor product of period polynomials. Okay. Okay. Now, if you look closer at this power series we had in this B-graded conjecture, then you see that these power series look like being the Hilbert-Poincaré series of some universal enveloping algebra, of some free algebra, let's say an algebra which is almost free, has a little bit relations. And so the point is that in the case of multiple zeta values, you were able to understand this Protos-Kramer conjecture in terms of this double shuffle and linearized double shuffle space, which then have relations to Ihara's action on coverings, on with the absolute Galler group and associators and so on. And somehow you have also here Lie algebras that are behind of this story. And I was talking too much, and so I will be brief for the next slides, because in the next slides I tell you how a mechanism of Écale allows you to define Lie algebras. And I'm sorry, I was telling you too much. Okay, so Écale has a theory of mools, and somehow this theory is living in the setup of non-commutative rings, and then it gives you some manipulations, and somehow this theory is very well suited to define and to study sets of multi-terms functional equations. And such terms occur somehow in the setup of this theory quite naturally. So you have this term of equation, you have something that looks like this symmetry we've seen for the generating series of multiple zeta values. It has kind of symmetries that look precisely as this kind of object that occurred by the product of these generating series. So you really see that the similar kind of formulas occur, and the upshot is that he is able to define Lie multiplication of these objects. And so essentially you have to think you have a family of functions which have an increasing numbers of variables, and now you multiply them with a certain substitution of these variables which are given by some recipe, which becomes quite messy. Okay. Now, I briefly tell you what we did with Layla, or what we are trying to do. It's like, now if you consider certain subspaces in this theory, then you can show that the restriction of this very general Lie law remains in this space. So you get really some smaller Lie subalgebra of the very big objects. And in particular, in these objects, you see all the stuff you had seen before or other people had seen before for multiple zeta values. And so some part is open. And so I'm finished now my quick run through this Ekal theory. So what do we have? We have these multiple q-zeta values. And we have this map by q goes to 1, with this appropriate factor, to multiple zeta. And then there is some relation to the so-called double shuffle Lie algebra. Okay. Okay. So essentially, what you're doing, you have your algebra, and now you divide out all products and all even terms. So you get a linear representation of the generators of this algebra. And the idea of Cartier and Racinet and so on was that on this space you have a Lie structure. And this is essentially this double shuffle Lie algebra you have here. And now this Lie algebra can also be described in terms of associators, and then you have this connection I was mentioning before to this Ihara stable derivation algebra. So you have this guy. And now you can even linearize these things, and you get this linearized double shuffle Lie algebra. And it is well known that this can be expressed in terms of this Ekal language. So this is what is Ekal language, and that this is isomorphic is in the thesis of Racinet. So you have this guy that is coming from motives and so on, can be just formulated in terms of combinatorics. And now, within this framework of combinatorics of Ekal, we can define these bigger spaces here. And we have nice candidates of Lie algebras that fit in this bigger space of Ekal. And I'd just like to indicate why we assume that these are the nice guys. And so essentially this means we get to this space by taking a central extension of this Lie algebra. Then on this bigger Lie algebra we have some derivation. And so we take the image and then we let the derivation go, and then we will get hopefully this new Lie algebra. So this is somehow what should be happen in the background. But how we get to this object, so we had this generating series, and now we just consider these identities modulo all the terms we did not understand. So it was these messy terms of lower weights and lower depths. So we just take them out, and then we know that if we take this out, then this decomposes according now to a vector spaces of these generators of this algebra. So we just changed the point of view. So we had this generating series for all the guys, and now we mod out the products. And so we get a much smaller series because we just set many of the coefficients to become 0. And now we just resort them, or each which just belong to one of these generators, and so we get a set of polynomials. And so this set of polynomials are the ones that are interesting, and you really, in small depths, you can write them, and you really see them. And so this Lie algebra is then the Lie subalgebra, which is generated by all these polynomials we get by modding out this generating series. And if you write them out, you get sequences of elements which satisfy certain many-term functional equations. But the point is here, you can really write these down, and you also, in depth 1, you get a precise relation which is somehow belonging to which bracket. So you have a nice set of these guys. And now, if you just look at the algebra that is generated by these guys, and also the relations you have on these, then you could just ask about the Hilbert-Poincaré series of these guys. And then you get some formula, which we now see the dimension of the space of period polynomials. So we had seen there was the even and the odd period polynomials, and by miracle, by the even you have a polynomial for the Eisenstein series, and for the odd ones you don't have. And actually it seems to play a role here, because it is just this dimension of all period polynomials that play a role. And so some of these relations you can identify coming from Eisenstein series and so on. And so the point is now, if there would be a kind of setup similar as in multiple zeta values, in the sense that you can identify the space of homomorphisms of formal multiple q-zeta values with some unipotent, some pro-unipotent algebraic group, and then you take the tangent space, which should be a Lie algebra, which should be this algebra, then you really would get an explanation why you get this nasty formula you were complaining. So the point is, you have this splitting of this algebra in the terms of these quasi-modular forms, and they have a rather nice generating series. And now you have these other guys by these generators, and you see, if you just write down this power series, then it's far from being obvious that it gives you this identity. It is clear once you multiply, it's an elementary algebra, but if you just look at this, and you won't guess this just by looking at that. That you really see that there's these generators in each odd degree, which then will be transferred by this derivation in going up in depth 2 case, and that you have these quadratic relations in yeah. So okay, and so how do these linearized partition shuffle Lie algebras look like? So it's like we now take all the polynomials where we mod out by quasi-modular forms, by products, and by lower depth terms. And then we get a set of very, very simple polynomials. So these are just, yeah, I think they are very, very nice and simple. And these then correspond to this B bracket. And furthermore, there's a natural map. If you have something in the partition Lie algebra, then if you just take the first non-vanishing coefficient, then it will be something in the linearized guy. And in particular, we get new generators if once we have a quadratic relation in this partition shuffle Lie algebra. So we had now this relation coming for every, at least from the number, from every period polynomial, we get a relation, and in particular, you see this relation, and this relation is exactly the relation that people attribute to the delta function. And therefore, you get this new object in this Lie algebra. And now, we could rephrase the conjecture. We had completely different in terms of a Lie algebra, which has some hopefully deep relations, but a priori now they just have some similarities. And to say, okay, if we look at this linearized partition shuffle algebra, then we have this generating series for this depth 1 guys. Then we had this period polynomials relation, we have homology, we have new generators, and we had some orthogonality, because in this description I said that we have this central extension, and of course a central extension gives you some orthogonality. And so you have this, and actually let's look what we had done. So we checked this, because now it's a purely combinatorial object we are dealing with. So we just take these polynomials and plug this in the computer and make programs, again parallel programming, and then let the computer run for a week in a very big machine. And you get that for much, much bigger range than we had for the Q series, that these Lie algebra will produce these dimensions. So we have this Lie algebra, it gives you precise the same dimensions, and there are some hints why this should be correspond to these multiple q-zeta values. And actually, if you look in this space, then there was this claim that there should be relations in depth 2 that comes with a square of modular forms. And so the title of this talk was Q, multiple q-zeta values and period polynomials, and at least I would like to use the last 8 minutes to show that there is in fact period polynomials. And so if you really write down these relations, then it turns out these are these polynomials in 4 variables which satisfy a long list of relations. And we have an additional datum that we have this symplectic Laplacian. And somehow Zagier was looking at these polynomials, and then he said, okay, let's first change it a little bit. You want to view this on matrices which have just the quadratic form corresponding to this Laplacian as determinant. So the determinant of this matrix is just U1 V1 plus U2 V2. So somehow you see the determinant, and now you play with harmonic analysis for this Laplacian. And now, if you use this notation, then this nasty functional equation become much more neat. Because now you have these matrices, the determinant of the matrix is not changed if you multiply with an element of SL2Z, and then you really see that you get something that is pretty close to the equations of period polynomials, but you have 2 more equations. And now the next observation is that all these equations here are preserved by this symplectic Laplacian. Therefore, we could just study these according to the harmonic analysis of those Laplacians. So we study by the kernel and by the image of the quadratic form of the kernel of k minus 2. And now, the kernel is given by matrices of determinant 0, and this we can get by this thing here. And now, if you just write down what we had on conditions, then we really see that this kernel corresponds now to sums of tensor products of period polynomials, so either in the plus or in the minus part, and it should be symmetric. This corresponds, I think, to this relation here, and that one is saying that the plus and the minus is preserved, therefore it is either in the minus or in the plus part. Yeah, I know. And now, if you use the formula for the dimension of this V minus and the formula for the V plus, and then you know how many relations you get here. So you just have various choices of you can make. You have the symmetry, so you sum over these numbers and really get the dimension to the square of the space of the modular form. So you really see these relations corresponds to tensor products of period polynomials, and they are there. And again, these other relations you can identify, and then you see that, okay, I'm quick, there's a second to last slide. You see that there's some intersection of this relation. This is a down-to-earth explanation of homology, and then these relations in the relations are at most as predicted by the formula. And so I'd like to finish by saying that we have now two objects, and they have very big coincidence, and we have seen period polynomials in both spaces, and I will be working hard to understand this more, and thank you for your patience.